Okay, thank you very much. Yeah, like everyone, I'm thankful to the organizers for this event and for inviting me. So the title is Three-Dimensional CFTs and Emergent Supersymmetry. It's based on this series of papers with a group at Princeton, including Simone Giambi and two excellent graduate students, Grisha Tarnopolsky and Lin Fei, who are not, some people go the extra mile, and my collaborators go the extra loop, so to speak, as you'll see. I want to just start talking about the importance of three-dimensional CFTs. They're certainly relevant to nature. In particular, the ubiquitous three-dimensional Ising model, which is described by the long-distance limit of Euclidean pi-4 theory in 3 dimensions, is relevant to many systems, and in particular to the water phase diagram, where there is this critical point, and near this critical point, it's in the universality class of the 3D Ising model. And in addition to this three-dimensional statistical system, there are also quantum critical systems in 2 spatial dimensions, which may be more relevant to what I'm going to be saying later on. Okay, so the specific phenomenon I want to address is emergent global symmetries. It's well known that sometimes renormalization group leads to infrared fixed points which have a higher global symmetry than in the original Lagrangian. For example, if you just take 2 scalar fields with arbitrary quartic potential, the most attractive IR fixed point will have O2 symmetry. It will be like phi1 squared plus phi2 squared. That's the most infrared stable one. And I'll talk about a more fancy version of this, which is what happens in 3-dimensional Yukawa theory with a kind of minimal field contact, which is 1 Majorana fermion and 1 real pseudoscalar. And this was conjectured by Scott Thomas to have emergent supersymmetry. Namely, not only is the field content supersymmetric, but it also flows to a n=1 superconformal CFT. That's basically the conjecture. I just now realized that this is the 2nd talk in a row, which is partly based on unpublished seminars at KITP. It's a coincidence. So in this theory, there is need for only one tuning, namely the fermion mass in 3 dimensions is forbidden by the time reversal symmetry, because psi bar psi is time reversal odd. So all that you need to do is tune the pseudoscalar mass to 0, and this kind of naturally happens at the phase transition where the time reversal is spontaneously broken. Basically, it makes a transition from 0 of f for this pseudoscalar to a non-zero of f. And this was conjectured by Thomas to flow to an n=1 supersymmetric 3D CFT. Now the UV Lagrangian therefore may be taken to be supersymmetric as well. It basically has only 1 dimension full coupling, and one can form the superfield sigma, which combines the real pseudoscalar and Majorana fermion. So it's a somewhat mysterious theory because it's strongly interacting. Some evidence for some confirmation of its existence, which is partial, comes from recent work on conformal bootstrap by these authors. But it's not totally sort of staring in your face because it requires tuning of some higher operator dimensions. And quite recently, a condensed matter realization has been proposed at the boundary of a topological superconductor, which the specific system they were talking about is something with helium-3, but I don't know too much about this aspect of the story. So this is the main player in my talk. Actually, it may not be totally obvious to you what this has to do with Gross-Neveu model. Just to remind you, it's originally was the model that Gros-Neveu introduced in 2 dimensions with this quartic interaction, we will think of these psi's actually as 4-component Dirac fermions. So we write this in, you can write this in 4 dimensions, for example. But in 2D, it has some similarities with 4-dimensional QCD. Namely, it is asymptotically free, it has a negative beta function, and the physics is somewhat similar to that of the 2D ON nonlinear sigma model with n bigger than 2, where there is a non-vanishing beta function. And what it means is that if you go to dimensions 2 plus epsilon, then both this ON model and the Gros-Neveu model have weakly coupled UV fixed points. And this is how this works. So there is an extra term epsilon g that gets added to the beta function, and since this is negative for n bigger than 2, the 2 can be cancelled against each other, and you have this expansion, the epsilon expansion of the coupling at the fixed point. And n is just 4, and f is actually the number of 2-component Majorana fermions in the game, which is the most minimal. So 2-component Majorana is the most minimal fermion you can have. And so using this idea, one can develop 2 plus epsilon expansions for various scaling dimensions. This was the work done long ago. It dates back to the 80s, early 90s. And you get these formula. You see that there are n minus 2s in the denominator, which, because n equal 2 is a rather special case where the model actually has an exactly vanishing beta function because it's equivalent to T ring for 1 Dirac fermion. But let's just take for now n bigger than 2, then you have this nice UV fixed point. And this is pretty analogous to what happened in the ON sigma model with n bigger than 2, which was studied in '73 by Brezan and Justin. Okay, so now to talk a little more about the ON model. This is classic stuff, but it's known that you can ask what happens as you push the dimension higher. Then it's better described by the ON linear sigma model, which is just a quartic field theory. And of course, in the seminal work in '72, Wilson and Fisher developed the idea of 4 minus epsilon expansion, because now there is an infrared fixed point. And this is much nicer. Right? Whenever you deal with a UV fixed point, it means you're dealing with a non-renormalizable theory. So it's always much nicer to have a UV completion. So basically what we have is that we know that the UV completion of the ON nonlinear sigma model is just the ON linear sigma model. And then you can ask the same thing. And actually this is, in practice, a very useful story, because since you know both the 2 plus epsilon and 4 minus epsilon expansion using these 2 models, you can then extrapolate between these 2 using Padé approximants, which is just ratios of polynomials in epsilon. And this gives you pretty good estimates for, or rather precise estimates for dimensions of operators, which only recently were exceeded by Bootstrap, but they're still quite precise. Okay, so what is the UV completion then of the Gros-Neveu model? And the answer was actually given in the early 90s by these authors. There were 2 independent papers. It's a very simple idea that what you really need to be talking about is just a multi-flavor Yukawa model, which people often call the Gros-Neveu Yukawa model. This is clearly the renormalizable model in 4 dimensions. So in 4 minus epsilon, this is there is a well-defined IR fixed point. Now there are 2 couplings, the Yukawa coupling and the quartic coupling, and you have to work harder to get these coupled beta functions. You get, again, nice formula. I just wrote a couple of terms. So to get this term, you need 1 loop to get, so this is the 1 loop beta function, this is the 2 loop, and you get these relations involving these complicated looking square roots and stuff like that. And you can similarly find the scaling dimensions by computing the dimensions and then setting G to G star. And then all the scale dependence drops out, and you get these nice epsilon expansions for simplest operators. This is sigma, this is the fermion, this is sigma squared, and so on. And as I'll show you, using these 2 the 4 minus epsilon and 2 plus epsilon expansions, one can actually compute very nicely the Padé approximants and get the physical value d equal 3 pretty well. Okay, another quantity that we care about is the sphere free energy, which is related to entanglement entropy across a circle in 3 dimensions. And actually with Simone Giombi a couple years ago, we got the idea to develop epsilon expansion for it as well. Namely, at first it seems hard, you have to work on a sphere in continuous dimension, but once you get in this game, you realize that it's doable. So the log z on SD is just a sort of raw partition function, but it's useful to multiply it by sine pi d over 2, because this quantity actually has poles near even dimensions due to the Weil anomaly. So for example, in 4 minus epsilon, this quantity has the structure A anomaly over epsilon, and to cancel this pole, you multiply it by the sine. Then everything works quite nicely, and you get very smooth functions, which interpolate between f values in odd dimensions, which are these universal entanglement entropies, and just the A and C anomalies in 4 and 2 dimensions. Okay, just to show you how this works, for free fields, free conformally coupled scalar, there are these nice formula. I won't tell you exactly how. You get them from computing determinants. They're very useful formula. And the sine pi d over 2 that used to be here just got cancelled by what we defined. And then you get perfectly smooth functions of dimension. And these numbers here are familiar. They're related to pi over 2 times just anomalies and A anomalies. Okay, what about the interacting theory? Then it gets more hairy because you have to also worry about curvature counterterms since you're in a curved space. So it's not enough to just introduce the usual renormalization. You need curvature counterterms. I won't give you the details of this, but in the end you get the rather explicit epsilon expansions for high order. And this was, I believe, work that Simone Giombi talked about at the last strings. You know, it's easy to make a mistake in this, but we have various cross-checks. For example, the large n limit can be computed in a different way. And then we use this to estimate, for example, the entanglement entropy for the Ising model for n equal 1, and got the answer that it's only a couple % below free scalar value, so it doesn't flow too far. But the 2 plus epsilon expansion in this ON sigma model is much more complicated, and we haven't developed it yet. One needs to deal with IR divergences. However, one can still fix the value in d equal 2, which is just known C anomalies for either n3 scalars, or for n equal 1, it's just the Ising model. And then everything is sort of under control. Now, what about the Gross-Neveu CFT, which again lives between 2 and 4 dimensions? We repeated this procedure, including curvature counterterms, and got this answer to order epsilon cubed. But now the difference is that in 2 plus epsilon expansion, you don't have any IR divergences. Everything is under good control, at least up to this order. And then this is, you usually don't think of Padé approximates as pleasant activity, but this actually works really well in the sense that different Padés give you answers very close to each other. And one can check this so-called generalized F theorem, namely that this F tilde in any dimension, as the theory flows from UV to IR, decreases. So here, for example, we look at the difference between interacting theory and the theory of n3 fermions, and you see that this is always positive, and this approaches nicely the large n limit, which we can get from the fact that it's a double trace interaction. So here is a summary for 3D Gross-Neveu CFTs, and just in case they happen to be relevant to some quantum critical points, you can vary n, 3, 4, 5, 6. So all of these work pretty similarly, and you see, so the bare dimension of psi is of course 1, so you see kind of the size of these anomalous dimensions. And you can also compute f over f of the free fermion theory. So here is a plot where we plot delta sigma versus delta psi. You see that as n increases, you approach the large n curve pretty nicely. There is a whole separate science of doing the 1 over n correction, so those are known too. And again, there was a long history in the 90s of developing their computations. And so now I'll talk about the special point n equal 1, which is sort of the most minimal case, but it may be in some ways the most interesting, because then you have to continue the model to a single Majorana doublet, and then something special happens with the Gros-Neveu model itself, because it just becomes trivial. Psi bar psi squared simply vanishes for a single Majorana fermion, and that means that there is no meaningful 2 plus epsilon definition of the theory. However, the 4 minus epsilon definition still works, and that's sort of the main point of our recent paper. It's a slightly formal definition because you have to, in 4 dimensions, you really have 4 component Majoranas, and you have to continue to half of it to get this n equal 1 model. But as you'll see, there is good reasons to believe in this procedure. So one is that this square root simplifies and just becomes 13, which actually turns out to be a lucky 13 here, because once you plug in this value, you see something nice happening, that the ratio of the 2 couplings becomes exactly 3. And that's consistent with this supersymmetric Lagrangian. So you see this supersymmetric ratio emerging, and this is the picture of fixed points. So you have just the free UD fixed point, then there is just the fixed point at T1 equal to 0, which is just decoupled 3D Ising and free fermion. And the most attractive one is this n equal 1 SUSY fixed point, where this ratio works. There is another more mysterious one, which I will not comment on too much, but it may also be interesting and may exist in 3 dimensions. Okay, so more evidence for emergent supersymmetry is that when you compute, when you go back to these general expressions and plug in n equal 1, you again see these rather magical things happening, namely that delta psi is delta sigma plus 1/2, delta sigma squared is delta sigma plus 1, and these are just the supersymmetry relations. And we checked them to order epsilon squared, which require 2 loop beta functions and 2 loop anomalous dimensions, but I don't see, I think a specialist probably can whip out these epsilon cubed terms as well, but we already have pretty strong evidence from epsilon squared terms. And so then we can do Padé. So now there is only one-sided Padé, because 2 plus epsilon doesn't make sense, but just Padéing d equal 3 results here, you get in d equal 3 a number which seems very close to the bootstrap hint for the supersymmetric point, which was obtained in this paper. I think theirs was like 0.582, that was their estimate. And another really interesting point is that in some sense the SUSY CFT exists for continuous dimension. So if you continue to d equal 2, what do you expect? Well, the guess is obvious. You expect the tricritical Ising model. And in fact, if you do Padé, you hit it very close. Like for example, you get delta sigma, which is close to 0.2, which is the exact dimension of the energy operator. And this sketch basically shows how operators in this 4D Yukawa theory continue to the tricritical Ising model. And it's amazing actually how close the central charge comes out. Maybe it's almost too good to be true, but you get 0.68 while the exact central charge is 0.7. Of course, this is, it would be nice to get some higher order corrections and see if this is as good as it seems, but this is what we see. Now there is an extension to models with U1 chiral symmetry. There is a Nambu-Yonah-Lasinio model, also often called the chiral Gros-Neveu model, which now has this more complicated quartic interaction. It has a U1 continuous chiral symmetry now, not just a discrete one. And so what's the UV completion of this model? Well, the answer is basically obvious. It's just another type of U-column model, which contains now a complex scalar, which is rotated by this phase under the chiral symmetry. And this was suggested at the end of that same Zinju-Sten paper. So we also developed a two-loop study of this model. And again, you see, so this model is, of course, constrained much more because there are chiral superfields in it. It has unequal 2 supersymmetry. So for example, the exact dimension of phi will be 2/3 in 3 dimensions. But you see very nicely how this U1 at the IR fixed point turns into the R symmetry of the model. And another thing is that this sphere free energy matches some earlier description that we developed based on SUSY localization for the Wess-Zumino model. So basically this NJLY model just flows to the Wess-Zumino model, which is the continued from 4 to 3 dimensions. Okay, what about going above 4 dimensions? So far we've been stuck between 4 and 2. What about above 2? Well, you can, for example, study ON model above 2 dimensions, and then it becomes again non-renormalizable, but you can guess a similar UV completion of this model. For example, in 6 minus epsilon dimensions, you can study ON symmetric theory, and this was done in, we did it to 3-loop order, and then Gracie did it to 4-loop. And you have obtained very nice matching with known 1/n corrections, and everything works kind of nicely. But the sigma q potential suggests that there is non-perturbative instability. So now let me end the talk with something maybe a little bit better, which also makes you believe in this business some more. So one of the motivations for I started studying these models partly because they also can teach you something about higher spin quantum gravity in ADS space. There is, of course, duality conjectures relating ON and GN models to Vasiliev theory in ADS space. Now, then there are similar conjectures relating models with anti-commuting scalars to higher spin gravity in de Sitter space by Ninas, Hartmann, and Strominger. And they looked at this original similar quartic model with SPN symmetry. So what we did in one of our papers is we tried to push this model above 4 dimensions by, again, making it UV complete. So it's non-renormalizable above 4 dimensions, but you can study a 6-dimensional model with 1 commuting scalar and anti-commuting scalars. So this model is, again, you can find the beta functions, this has IR stable fixed points, but now this model is kind of non-perturbatively stable because the couplings at the fixed points are imaginary. So it's a lot like the original Fisher's paper on phi-cube theory in 6 dimensions. It gives you non-unitary theories, but they're perfectly stable non-perturbatively because the path integral just oscillates. And then you have some special symmetry enhancement for n equal 2, which is reminiscent of what I said earlier in the talk. You have a model with theta and theta bar and sigma, and magically at the fixed point you have enhanced supergroup OSP12 symmetry. One manifestation of it is that the epsilon expansion of sigma and theta dimensions, which are different for general n, for n equal to become exactly equal. So this gives you a kind of nice supergroup symmetry enhancement, which can be done like by any student of field theory. And this turns out to be related to a continuation of the Q-state Potts model to Q equals 0. There is this classic work by Zia and Wallace on Q-state Potts model in 6 dimensions. It becomes renormalizable in 6 dimensions. And if you take the 6 minus epsilon expansions, continue them to Q equals 0, you get exactly the results that I showed to you before. You get exactly these formulas. So they coincide with the 0-state Potts model. So in this case, we basically know what is the statistical system behind this enhanced symmetry state. It's a zero-state Potts model, which there is a lattice model called the spanning forest model, which is one of the really basic lattice models. And the Monte Carlo results, this model actually has phase transitions in second-order phase transitions in 3, 4, and 5 dimensions, which are reproduced pretty well by epsilon expansions. There is this paper by Alan Sokol and collaborators on this. So in this case, we both know the field theory and know the sort of statistical system behind it. And the dream would be to guess the condensed matter systems behind the other symmetry-enhanced points. So let me conclude. Basically, this old-fashioned technique of epsilon expansions in ON, Gross-Nevu, Naboyana, Lasinio, and other CFTs is actually very useful for applications to some condensed matter and statistical physics. They can provide checks and balances for bootstrap numerical results or hints for which theories exist, approximate scaling dimensions. There are also nice playgrounds for RG inequalities and higher spin ADS CFT. And the thing that I stressed in this talk, that something special can happen at low end, where there are enhanced IR symmetries, including boson fermion symmetries, like supersymmetry or supergroup symmetry. And in particular, some very simple Yukawa CFTs in d less than 4 exhibit this emergent supersymmetry, which you can study order by order in epsilon expansion. And the hope is that these can be realized in condensed matter systems, and perhaps even something can be measured along these lines. Thank you very much.
Did the 5-4 coupling have the right sign at the fixed point?
At the SUSY fixed point, it has a stable sign.
So in the 4 minus epsilon dimensions, your fixed point had positive 5-4?
Yes. Yeah, there are actually 2 fixed points. The SUSY one is perfectly stable. So let me try to go back. Yeah, I have this phase diagram. Well, this is for radical 2. Yeah, this is for radical 1. So you see the SUSY one, the G2 is positive. There is another fixed point which is just related by the other branch of the square root. There are basically 2 solutions. This one looks unstable in 4 minus epsilon. But we're still taking it somewhat seriously because the bootstrap suggests the existence of 2 theories, one supersymmetric one and one non-supersymmetric. So the hope is that this somehow, when you continue it down in B, it stabilizes. But I mean, this is much more speculative. This one looks incredibly solid, and the existence of tricritical easing also makes you kind of a believer in this whole extrapolation.
So for the Wilson-Fisher fixed point, one may hope that in some sense it's non-perturbatively defined even for fractional d. These fermionic theories, do you think they're also defined for fractional d non-perturbatively? In particular, I'm worried about the evanescent operators. There are infinitely many 4 Fermi operators in fractional d.
Yeah, but I think since we're dealing with a renormalizable Yukawa model, I hope there won't be any trouble. I think it's more the trouble for defining it with 2 plus epsilon expansion. Then there is a fear that at some high enough order you generate evanescent operators even at the Gross-Nevu model. But I don't know the full answer, but I think this works so well. I mean, that hopefully they're basically worried about some irrelevant operators
Yeah, at the full Fermi level, there are already immediately infinitely many operators in fraction P. So this is different from the scalar theories.
Right. Well, I don't have a great answer to this.
Last question. Well, if not, let's thank all the speakers for this session.